What's up, guys? Today we'll be doing the code walkthrough of creating your own PDFL control loop class. This video is based on the previous video where I explained what a PDFL is, and I'm kind of just going to be jumping through that real quickly. So if you haven't checked that out already, make sure to do so. All the code in this video will be included in the description. However, there will be a small typo/error within it that will not cause an error, but it will not function properly. So it's up to you to discover what that error is and fix it yourself. I think this is a really important process to master when moving your algorithm from concept to code. And so I want to make sure you guys have that skill set too. That being said, I'm going to be using my own sort of coding process. A lot of people use this in the industry, but it is debated which way is better to code. When going from a conceptual algorithm to code, this is the way I like to do it. I just find it easier to test, easier to mentally walk through, that sort of thing. With that being said, let's jump right in. So the first thing is we're probably going to want an object. So we're going to make a class and we're not going to make it static. So the first thing we need is a constructor because we want a way to pass in our four control constraints. So let's just start by doing that. And it's going to take in 4 arguments. We need our P, we need our D, we need our F, and we need our L. And for right now, that's all we're going to do with the constructor. Now, the next thing we need a run function. And what this function is going to do is it's going to take in the error and it's going to give us back our response. So public double run, and it's going to take in an error. Simple enough. And if you remember from the previous video, all we need to do is sum up these 4 components and then add them together and return it. And that's effectively our run function. So in order to do that, we're going to have to create the functions that handle each of these individual constraints. So starting off, let's make a private function for the P component. And that's going to take in an error. And make it return 0 for now so it's happy. And we have our D component. And that's going to take in a delta error and a delta time. Awesome. And then we have our F component. And that's going to take in nothing, actually. Simple enough. And then we have our L component. And that's going to take in the error. Return 0. So now, if we just say P is equal to P component, D is equal to D component, F is equal to F component, and L is equal to L component, we can get our response. And that will be equal to P plus D plus F plus L. And then we want to return our response. Boom. Awesome. Now, let's go ahead and fill out each of these individual components to make sure they do what we actually want them to do. So for the P component, pretty simple. Our response is just going to be, we do need our constants first, not to get ahead of myself. So we want these constants to be accessible to the class as a whole, and no reason not to. So we'll just make them private doubles, and we'll have the same thing just passed on. And then we'll do this.kp to get this one, and we'll set it equal to this one. So then this.kd equals kd, this dot kf equals kf, and this dot kl equals kl. Awesome. So our response is simply kp times error, and we want to return our response. Now for the d component, this one's a little bit more complicated. First, we need to find the derivative, which we can approximate by doing the delta error divided by the delta time. And then our response is going to be equal to the derivative times the d component, and we want to return our response. And then the f component, super simple, but for structure's sake, we'll also do a little response variable that's just going to be equal to the feedforward value. We want to return the response. And then the lower limit component is a little strange. Probably uses a function you've never seen before, or at least hopefully you've never seen before, called signum. So math.signum. And what it does is it returns the size, it returns which direction this value is in. And essentially what that means is if this value is negative, then it will return -1. If it's positive, it will return 1. And if it's 0, it'll return 0. So actually, let's break this down a little bit more just to make it clear. So we have our direction, and that's going to be equal to the signum function. And if we do our direction times our lower limit value, then we get our response. And all we want to do is return our response. Simple enough. So now all we need to do is fill out these things up here, and we should be done. So as for going about creating these things, this one's just error, that one's just error, this one's nothing. So simple enough, error, error. And now all we need to do is deal with the d component. So one option is to take the error and time from the previous loop and then use that to get your delta time and delta error. I found this to be a little bit sporadic, so I like to use a ring buffer of 3. That's just worked for me. You're welcome to try out different things, but that being said, I want to show you what was in the video in the previous video. So let's go ahead and do that. We need 2 things. First, we need the timer. So let's create our timer. Timer equals new timer. And then we're going to want 2 ring buffers, one for the timer and one for the error. So let's do time buffer. That's going to be equal to new ring buffer. And we want length of 3 and initial value to be 0. And very similar thing. So let's just copy that for the error buffer. So the timer time, we'll call it timer time, is going to be equal to the timer dot get time. And then we're going to shove it through the buffer. So previous time is going to be equal to the time buffer dot get value, and we'll give it the timer time, keep it updated, and then previous error, let's just simplify this to time actually, is going to be the error buffer dot get value error. So now to get our delta time, we want delta time. That's just going to be time minus previous time. And then delta error equals error minus previous error. So let's go ahead and feed that in here. So I think delta error was first. Yes, and then delta time. And boom, that should be our PDFL control loop. Now there are a couple things I like to add on top of this because in theory this would work, but it's a little shaky. The first thing that comes to mind is we want to make sure our timer is reset as soon as we want it reset actually a lot of times. So let's go ahead and create a little function for that. So we're going to might as well make it public because why not? Reset. And essentially all we want this function to do is sort of like bring us back to our initial state of zeros. And the reason why we have zeros here is because in terms of the derivative, it'll essentially make it 0 for the first couple of loops, which is fine because we only have 3 loops here. But that gives us security in case, like, let's say we run the PID in an extreme condition and then all of a sudden we don't run this error function until 10 seconds later. If we have some crazy starting value, then it could give us some crazy D component and give us some wild error. So one thing, our reset function is going to do 3 things. It's going to reset the timer. And then it's also going to reset our buffers. So we'll do time buffer dot fill, then we'll just give it zeros, and then same thing with the error buffer. So as I mentioned earlier, if we don't call this loop for a while, we're probably going to want to reset the buffer. So what I like to do is you say if delta time is greater than some value, let's say 200 milliseconds. Then what we're going to want to do is we're going to reset the system, and then we want to return essentially rerunning this function. And essentially all this really says right here is if the PID hasn't been updated, oh, no. If the PDFL hasn't been updated, reset it. Another thing is, as we discussed in the previous video, the lower limit component keeps the system moving no matter what. And that's important when we want to reach a target position. But once we're in a target position, we don't really want it to keep moving us no matter what, because that means we're going to get a lot of oscillation. So it means we need to incorporate a dead zone. Luckily, I've been able to use a dead zone of 5, and it's been just fine. And 5 ticks is going to be perfectly accurate, not noticeable at all. So let's just go ahead and put that in here. I like to add this as a separate component, but you can do this however you wish. So we'll do like a public function that lets us set our dead zone. So that will take in a dead zone. And dead zone. It will set this dead zone to dead zone. And so if our error is within this dead zone threshold, so let's go ahead. If error is less than the dead zone value, then we don't want the lower limit component anymore. So let's go ahead, let's do it like this. Actually, our response is just going to be the same response, but without lower limit. The last thing that I like to incorporate is a homed position. So this may not always be the case, but in terms of slides specifically, when you bring them all the way down, you want them to have a little bit of negative value. Some ways we have addressed this in the past is by setting the error to be greater than it actually is so that the system keeps pushing down. But often this value is going to be extremely small and we just want it to keep that bottom position. So I like to add in a little homed value. So we can do our public void set home threshold, or set homed. And we're going to want this to set a Boolean within the class, which will be homed. And we'll say boolean homed, and then this dot homed equals homed. And we can kind of just override this entire thing, where if we are homed, then we want our response to be a homed constant. And then we want to be able to set that homed constant as well. And so normally what I do is I make this value like minus 0.1 so that the slides are just pushing into the chassis a little bit. That way they don't bounce up and down while it's homed. Another way to restructure this class would be to just pass in a current position and then have a target position as well. And then you can handle this Boolean of if homed within the class itself. That was something we did, but it's a preference thing as to which way you do it. But yeah, besides that, the only other thing you might want to incorporate is a little way to update your constants. So we can do update constants, which is super useful for tuning. So we'll go ahead and actually just copy this entire thing. And that's it. This should be your PDFL control loop. One important thing to consider, especially when it comes to this homed constant value, is if you're driving your motors incorrectly, this can lead to them burning out or your robot restarting, all sorts of terrible kinds of things that you don't want to happen in competition and that I've seen happen at the highest level. So make sure to stay tuned for our upcoming video where we're going to be describing how to properly drive your motors so that this never happens to you again.